Okay, so in the last couple of lectures, we introduced our Euler totient function, phi of n. Phi of n, remember, it gives you the size of Zn, the multiplicative group of congruence classes modulo n. Okay? That's one way to think about it. And when we investigated the group properties of that, we found that in order to form a group, we could only allow, or we could only consider those congruence classes of integers a, where a was co-prime to n. Okay. So this group Zn was the superscript of multiplication, so the multiplicative group of congruence classes, sorry, the congruence classes under multiplication. When we consider only those congruence classes that are co-prime to n, then we have a group, okay? Because those ones have multiplicative inverses. So we'd like to have an understanding of the size of this group. So phi of n, by definition, is the function that gives you the size. We can evaluate phi of n. This is review. We can evaluate it by working off the definition. So if somebody throws an n at you, you can work out phi of n by examining all the numbers up to n and seeing which of them are co-prime to the n that you have, and that's your value of phi of n. But that feels a bit naive, and you're just checking, especially if n is large. You've got an awful amount of cases to check, and you're not really learning anything about the structure or the behavior of phi. Okay. So we'd like a better way of evaluating phi. Okay. On computer. And indeed there is one. Okay. So this is the product formula for the Euler totient function. Okay. And this is theorem 5.1. So this is really the main result of this chapter, that this chapter is heading towards proving. It's establishing this formula for phi of n. Now, it's a product formula, so it's a capital pi. So it's a product of all these terms. These terms involve pi's and ai's. Okay, so what are they? Well, the pi's and ai's come from the prime factorization of n. Okay, so we're familiar from our earlier chapter on primes that every integer factors uniquely into a product of primes. And we have this canonical way of writing the integer n as the product of these powers of prime. Okay. So p1, p2, all the way up to pr, those are the distinct prime factors that n has, and ai are their respective powers in the factorization of n. And the value for phi of n is given by a related product. We have to reduce each of the powers on each pi by 1, reduce it by 1, and then we get an extra factor, which is 1 less than pi. We get one of those for each of the distinct primes, p1, p2, and so on up to pr. Okay. Now, what's involved in proving this? Well, you can kind of write down the overall argument quite quickly on paper, which says that phi of n, well, it's equal to phi of, so n you think of as its prime factorization. Okay, so we want to find out phi of n, so we want to find out phi of this product. Well, the first thing we're going to do is interchange the order of the product operation and the phi. So we're going to say that phi of the product is the product of the phi's. And then we're going to use the fact that each of phi of a prime power we get by reducing the power by 1 and multiplying that into pi minus 1. Okay? Now that, in a few lines, is the proof of theorem 5.1. Okay, but you've got to ask what justifies each of those jumps. Okay, the first, going from left to right in the top line, is just replacing n with its prime factorization. So that's, just using the fundamental theorem of arithmetic. What justifies this last step? Well, we proved that the other day. That was where is it? That was lemma 5.2. So this step, going from the middle line down to here, this was lemma 5.2, okay, which we proved the other day, which said that phi of a power of a prime is given by this expression here, reducing the power by 1 and multiplying by this factor, which is 1 less than the prime. Okay. So this here is just an application of lemma 5.2. So this was proved previously. Okay, the proof of it is in the notes. We talked through it last time. The other part of the argument, which we haven't justified yet, is this line. So what allows us to say that phi of a product is equal to the product of the phi's? Okay. You can't just, I mean, it looks appealing behavior that phi of a product is equal to the product of the phi's, but it's, you know, it's not true in general for general functions. For instance, if instead of phi of this we were talking about the integral of a product of functions, well, you should all know, I mean, we should all know that you cannot integrate a product of functions by just taking the product of the individual integrals. Integration doesn't work like that. It does work like that if this was the summation operation in the middle. The integration, the integral of a sum of functions is the sum of the integrals. So sometimes you get this nice behavior that you can interchange operations with functions or transformations. So what specifically allows us to do this here? So this step is true since phi is multiplicative. And this is what we're going to prove today. Okay. So once we proved this lemma 5.2 previously, we're going to prove this fact today that phi is multiplicative. So then that will be the proof of theorem 5.1. It's laid out slightly differently in a kind of an induction way in the notes, but essentially it's just this argument. Instead, I approach this interchange of these operations in a bit more of a formal way using induction. But it's essentially that idea. So we're going to prove today that phi is multiplicative. Now, what does multiplicative mean? It's an important property that functions in number theory can have. So this is the definition of the term multiplicative. I write it out here for phi, but it's a property that can apply to lots of other functions as well. A function is multiplicative when phi of a product a times b is equal to the product of the individual phi values. If your function acts like this for every single a and b, then it's called completely multiplicative. If there's no restriction on the a and b, and your function always behaves like this, it's called completely multiplicative. That's like extremely well behaved. But it's so well behaved, it's not really that interesting. Functions that are completely multiplicative are kind of quite easy to understand because they display such nice behavior. But when we use the term multiplicative in number theory, we're meaning a function that behaves like this under the assumption that the a and b, so it's not just any old a and b, but we only ask for this nice behavior when a and b are co-prime to one another. When a and b don't share any common divisors apart from 1. So phi being multiplicative means this is true for every pair a and b whenever the GCD of a and b is 1. It's equal to this, it has this property whenever the greatest common divisor of these two factors a and b is equal to 1. In particular, what kind of things can be co-prime like this? Well, in particular, different powers of primes powers of different primes will be co-prime. So the way it's used to prove the product formula, which we have at the top of the page, so in particular, if P1 is not equal to P2 are distinct primes, then the greatest common divisor of any power of P1 and any power of P2, that's going to equal to 1. Okay. Being co-prime means you don't share any common factors or any common prime factors. So powers of distinct primes are certainly examples of pairs A and B which are co-prime. Okay. So in order to make that first move from the top right-hand side down to the middle right-hand side, we'll be applying the fact that this function phi is multiplicative. Okay. So phi evaluated on this product of co-prime factors, each of the factors being the power of the prime, you can split that up as the product of the individual phi values. Okay, here it's just quoted as for a product of two things, but using induction you can extend that to a product of any number of things. Here you just got a product of two factors. Here we got a product of r factors. We're taking the product over I equals 1 up to r. So that's the definition of phi being multiplicative. Okay, we have to prove it. So this is going to be the task that we're going to work through now. But you know, apart from the details of proving that phi is multiplicative, which we'll talk to now, is there any queries about the way we put it together, the other lemma, and the way we established the product formula? Any queries about that, or anything that could clarify on that? This is an interesting property, being multiplicative, and it's shared by lots of other interesting functions in number theory. But we're just focusing on the Euler totient function. Okay. So, how to prove that phi is multiplicative? This is the result of lemma 5.5. Okay, so let's get the notes up on the screen. So here we have it, lemma 5.5. Okay, it's a big block of text there, but I'm going to talk through it and illustrate the main points. Now, in preparation for it, we've got some lemmas to do before this lemma. Okay? So lemma 5.5 is proving that phi is multiplicative. But before we get into the details of that, we want to establish a couple of results concerning a couple of results that will be useful for proving that phi is multiplicative. And it's a couple of results about linking together greatest common divisor and congruence classes, and then just a little detail about how greatest common divisors work. Okay? So this first result, lemma 5.3, it's actually a previous exercise we've already proved. We would have done this either in the lecture or in the tutorials. So it's a very nice result, and it links together the concept of greatest common divisor with congruence classes. And it shows that they link together extremely nicely, okay, in this way. If you're talking about a modulus n, and you've got two representatives of the same congruence class, so an A and a B that are congruent modulo n, there are a number of different ways of thinking about this. That means n divides the difference A minus B, or it means when you divide A and B by n, you get the same remainder. A and B differ by a multiple of n. There's lots of different ways of phrasing it. But A and B are two representatives of the same congruence class. They're congruent to one another. If that's the case, then really nicely, when you take their greatest common divisor with n, you get the same value. Okay. So if you're in the same congruence class modulo n, you've got the same greatest common divisor with n. Okay, that's nice to know. And this property here, we've kind of proved half of this in an exercise. But this says, okay, this talks about the greatest common divisor of U with a product VW. It says that U is co-prime to a product VW if and only if it's co-prime to V and co-prime to W. So U, think of U as U, you are co-prime to a product, V times W, if and only if you're co-prime to V and you're co-prime to W. Okay. So being co-prime to a product is the same as, exactly the same as being co-prime to each of the factors in the product. mean, a little example. Well, one way to think of this is quite easy to think about when you think in terms of prime factorizations. Okay? So U has a certain prime factorization. Okay? Write U as a product of primes. V times W will have a certain prime factorization. Now, prime factorizations are unique, so that means the factorization, the prime factorization of V times W will just be the product of the prime factorization of V and the prime factorization of W. You just glue the two together, that gives you the prime factorization of V times W. Saying two things are co-prime means that their two prime factorizations do not overlap at all. They don't share any common prime factors. So this statement on the left of the equivalent says that U is co-prime to V times W. So U, the prime factorization of U is completely different to the prime factorization of V times W. But that's the same as saying that U is completely different to the prime factorization of V. There's no overlap between the prime factorization of U and V, and there's no overlap between the prime factorization of U and W. Okay. So it has a nice understanding in terms of prime factorizations. Now, the proof of this preparation lemma, lemma 5.4 that we've got in the notes here, doesn't rely on that. Instead, it proves it using, it doesn't talk about prime factorizations. It just talks about greatest common divisors and linear combinations. So lemma 5.4 is an equivalence. These two statements, one on the left and one on the right, are equivalent. So it goes both ways. One of the directions we've already proved was a previous exercise, an exercise from chapter 2. That was the direction that said if U is co-prime to V and U is co-prime to W, then it's co-prime to the product, V times W. So that's the previous result we've already done. The other direction falls out pretty quickly as well. So here, for this other direction, going left to right this time, we assume that this is true. We assume that U is co-prime to V times W. And then immediately we pass to an equivalent statement. That means that there exists a linear combination of U and V times W that is equal to 1. Okay. Remember, we link together very strongly the ideas of two numbers being co-prime and there existing a linear combination of them equal to 1. So if U is co-prime to V times W, there's a linear combination of U and V times W that's equal to 1. But then this very linear combination, you can look at this in a couple of other different ways. You can instead consider it as a linear combination of U and V. You can collapse the beta and the W together as the coefficient of V. So this is a linear combination of U and V that's equal to 1. Therefore, U and V are co-prime. And then if you just change your view of it, you can also think of it as a linear combination of U and W. Something times U plus something times W equal to 1. So it also says that U is co-prime to W. Okay. Two things having a linear combination equal to 1, that's the same as those two things being co-prime. Okay. So that spelling that out, which is done in those 3 lines there, there's 3 different ways of looking at this linear combination. It shows you that this left-hand side implies that on the right-hand side. Okay. So those are our 2 preparation lemmas. If you're in the same congruence class modulo n, you've got the same greatest common divisor with n. Secondly, being co-prime to a product is the same as being co-prime to each of the factors in the product. Any questions about those lemmas? So those are our 2 kind of tools, 2 ingredients that we're going to put together to prove that our function phi is multiplicative. So we're going to prove that phi is multiplicative. We're going to do it directly. So to prove it's multiplicative, we have to establish this formula. The phi of A times B is equal to phi of A times phi of B. and we're assuming that A and B are co-prime. We're going to do it directly. So we're going to consider all the numbers between 1 and AB minus 1. Sorry, all the numbers between 1 and A times B. Sorry. And we're going to count how many of them are co-prime to n. Okay, we got this modulus n floating around. No, sorry. Sorry. I misspoke. We're looking at the numbers in this range, 1 up to AB. And we're counting the number of them that are co-prime to AB. That's the left-hand side, phi of A times B. And we're going to count them in such a way that shows that the number of things in this list that are co-prime to AB is equal to this product. So there's no funny kind of proof by contradiction or induction proof or anything. We're just going to lay it out and prove directly that the left-hand side is equal to that. Now we're examining this list of integers between 1 and AB. We don't think of it as one long list. We think of it laid out in a grid. And of course, the natural way to lay it out, since we're talking about all the numbers between 1 and A times B, it's natural to lay it out in an A times B rectangle. Okay. So we lay out all these numbers, 1, 2, 3, 4, 5, 6, B plus 1, B plus 2. Okay, so we lay it out in a rectangle grid of A rows and B columns. The columns are indexed 1, 2, 3, up to B. So there's B different columns. And the rows are, well, you can think of the rows as indexed by the multiple of B here. You got 0 times B in the first row, 1 times B, 2 times B, 3 times B. You end with A minus 1 times B. So we're indexing the rows from 0 to A minus 1. So you got A rows. A rows and B columns. Here are all the numbers between 1 and A times B. And it turns out that this way of laying them out is very suitable to the kind of counting that we want to do. Okay. So first of all, yeah, maybe I'd just like to make some notes over and above what's in the printed notes there. I'll switch to the document camera. So I just want to repeat out that grid a bit. I just want to draw on top of it a little bit. You go 1, 2, 3, 4, B minus 2, B minus 1, B. Those are the column headings. And you have B plus 1, B plus 2. This will end with 2B here, so you've got 2B minus 1, 2B minus 2, etc. I'd like to put in the next row, just add a little bit more detail, 2B plus 1, 2B plus 2, etc., etc. And this will end with 3B minus 2, 3B minus 1, 3B. You keep going like this until you reach, well, let's put in the second last row to make it a bit more detailed. You'll have an A minus 2B plus 1, A minus 2B plus 2. They become a bit long, don't they? A minus 2, oh no, this is going to be A minus 1, B minus 2, A minus 1, B minus 1, A minus 1 times B. Then you have the very last row, which will be A minus 1 times B plus 1, A minus B plus 2, etc. And this will go up as far as AB minus 2, AB minus 1, and then it will end with AB. There's a little bit more detail. We've got B columns, A different rows. I just lifted that one up to avoid that one. A different rows. So how many things here? This is the question. We search phi of AB. Phi of AB equals what? Well, what that means is how many integers here are coprime to A times B. So asking what A5AB is asking this question here. How many integers here are coprime to A times B? We're using one of the lemmas we've just introduced. This question becomes, how many integers here are coprime to A? How many are coprime to A and B? Okay. That result there we're using is lemma 5.4. Asking for something to be coprime to the product A times B is exactly the same as asking for it to be coprime to A and coprime to B. So this is lemma, that step is justified by lemma 5.4. Okay. So now, of all these numbers here in this grid, we're looking for all of the ones that are coprime to A and coprime to B. So first of all, firstly, where are the integers coprime to B? Where in this grid do the integers live that are coprime to B? Well, in answering that question, we begin by making an observation. So look at all these numbers in the first column. 1b plus 1, 2b plus 1, etc. All of these numbers here are congruent to 1 modulo b. Yeah? Because they're all a multiple of b plus 1. Every number in the second column is congruent to 2 modulo b, because they're all a multiple of b plus 2. First one is 0 times b plus 2, b plus 2, 2b plus 2, etc. All the way down to a minus 1 times b plus 2, be the one sitting here, which I haven't written it. It's the same for every column. Okay. So when you look down a particular column, everything in there is in the same congruence class modulo b. Okay. Now across the top, we've got the integers between 1 and b. So we know that how many of those are coprime to b? Well, we know that there's 5 of b is the number. Okay. So note, within a column, everything is in the same congruence class modulo b. Okay, within a column, everything is in the same congruence class modulo b. Columns are indexed 1 through b. And so 5 b of them are coprime to b. Contain integers, all coprime to b. So I want to make sure you follow what I'm saying there. Okay, we're speaking generally, so it makes the sentences a little bit awkward, but I've got b columns across the page there. They're indexed by the complete set of residues modulo b. The integers 1, 2, 3, all the way up to b. And within one column, when you look down the entries in the column, you see that all the numbers are congruent to each other within that congruent modulo b. And remember, the lemma 5.3 said, Well, if everything in this column is congruent to each other modulo b, that means they all have the same greatest common divisor with b as well. So there we're using lemma 5.3. If everything within a column, they're all co-prime to each other modulo b, then they all have the same greatest common divisor with b. Okay. So you ask yourselves, how many of these columns have a greatest common divisor of 1 with b? Well, by definition, the answer to that question, how many of these columns are co-prime to b, the answer to that question is 5b. By definition, okay? Because 5b is the number of numbers between 1 and b that are co-prime to b. Okay. I don't know what that actual number is, because I don't know what b is. B is general. But somewhere here, there's a bunch of these columns which are all co-prime to b. Well, I do know that 1 is one of those. So the first column, everything here is co-prime to b. All of these integers are co-prime to b. If b is an odd number, then all of the second column will be co-prime to b as well. But there's a bunch of columns here. How many of them are there? There's 5b. They are all co-prime to b. Now remember, if you look up here a little bit, I'm trying to answer this question. How many integers are co-prime to a and b? So what I've done is, conceptually, I've located all the ones that are co-prime to b. So the ones that I'm trying to count in this question will come from these columns that I've highlighted. The 5b columns that are co-prime to b. But now we do the same consideration that we've gone through there, but just with reference to a. Okay. So secondly, where are the integers co-prime to a? So this time we don't look down the columns, this time we look across the rows. When you look across one of these rows, well, for a start, no, hang on. No. Sorry, rephrase that question. Rephrase this question. Within these columns, within these 5b columns that we just highlighted, how many elements are also co-prime to b? Sorry, co-prime to a. Let's just look at the first. Let's just look at the first column. All of these numbers are co-prime to b, but how many of them are also co-prime to a? That's the question. How many of these numbers are co-prime to a? Now, first of all, how many numbers are there here? Well, they're indexed by the multiple of b, and it goes from 0 up to a minus 1. So there's a different numbers here. Then we ask ourselves, well, how do they fit with regard to the congruence classes modulo a? Okay, so let's switch back to. I want to switch back to the note. We're looking at this first column, say, or any one of the highlighted columns which are co-prime to b, and asking ourselves how many of the things in there are also co-prime to a. Okay, so this takes us to this section in the proof. The task now becomes to decide how many integers in these co-prime columns co-prime to A. So let's look at one of the columns. I was talking there about the first one. That would be where R is equal to 1. So R is one of the small remainders modulo B. R goes from 1 to B. Indexes the column. If we pick one of those columns, okay, it's headed by an integer R. These are all the numbers it contains. R, B plus R, 2B plus R, etc. There's A of these numbers here. Okay? 0, 1, 2, counting up to A minus 1. There's A different numbers here. And actually, I don't know which one is which, but the A different numbers listed here, they represent all of the congruence classes modulo A. The A different numbers that there are here, they're all different modulo A. Now that requires a little proof. Okay, and the proof of it is a little proof by contradiction, a little quick proof by contradiction. Suppose that two of these were not co-prime, not distinct modulo A. So suppose we had a VB plus R and a WB plus R. Two of these numbers, all of these numbers are something times B plus R, something times B plus R, and something else times B plus R. Suppose you had two of them that were congruent to each other modulo A. Could that happen? Well, by definition of congruence, that means A divides the difference between them. And the difference between these two numbers is B minus W times B. One of these numbers minus the other one, the R's cancel out. So you've just got B times the difference between B and W. But now, key assumption at the start of this proof is that A and B are a co-prime pair. So here we've got A dividing a product. One of the factors is B. Euclid's lemma tells us then that A has to divide the other factor. You've got A dividing a product of B times something else, but the A and the B are co-prime. That means A must divide the other factor. So how can A divide B minus W? What are the options for B minus W? B minus W are two numbers from the range 0 through A minus 1. How can those have a difference that's a multiple of A? Because they're both trapped. They're both trapped between 0 and A minus 1. When you look at how far apart two numbers between 0 and A minus 1 can be, at most, they can be at most A apart, at most A minus 1 apart. Okay? Because they're coming from the range 0 through A minus 1. So the only one of those differences that's divisible by A is in fact the difference 0. Okay? The only way you can take two numbers, V and W, in this list of coefficients of B from 0 through to A minus 1, that differ by a multiple of A is when you actually take the same index, the same coefficient twice. But that can only happen when V is actually equal to W. But that means you're talking about the same number. And obviously, every number is congruent to itself. Modulo anything. So that means that of the A numbers that are listed here, they're all different from each other modulo A. So that means we're looking at representatives of all of the congruence classes modulo A. So then we return to that last question we posed to ourselves on the sheet. How many of these are also co-prime to A? Well, if that's a complete set of residues modulo A, then the answer to how many of them are co-prime to A is 5A, by definition. 5A is the count of the number of congruence classes modulo A that are co-prime to A. This is a complete set of residues we know now, modulo A. So 5A of them are co-prime to A also. So let's just summarize. It's the whole argument is summarized in this last paragraph. We set out the array in figure 5.1. So that was that rectangle of integers in the notes and we drew on the page. A rows and B columns. They're all the integers between 1 and A times B. We're looking to evaluate phi of A times B. We're looking to count the number of numbers there that are co-prime to A times B. By one of the lemmas, that's equivalent to saying how many of them are co-prime to A and B. We first tried to pin down the ones that are co-prime to B. We found that they had to organize themselves into columns. So there's a certain collection of columns that were all co-prime to B. How many of those columns were there? There was phi of B was the number of those columns. Then when you looked within any one of those columns, we saw a complete set of residues modulo A. So how many of those are, in addition, also congruent, so also co-prime to A? The answer to that question is phi of A. So how many of the things in the picture are co-prime to A and B? Well, you have to look at, you count phi of B columns, and within each of those columns, phi of A of them are co-prime to A also. So that gives you the product answer there. It's phi of B times phi of A. Phi of B columns, within each of those columns, it's only phi of A of them that are also co-prime to A. So the answer in total is going to be phi of B multiplied by phi of A. So that establishes the proof of that. So that means we can now. That means we've now proved all the steps in this argument for the product formula. Knowing that phi is multiplicative, that justifies this move of interchanging the order of phi in the product operation. Each of these different powers of a prime are co-prime to one another. Primes are distinct. So phi of that product we can replace with the product of the phi's, and then phi of a prime power we established last time was equal to this expression. So that proves that very nice product formula for the Euler totient function, which is based on the prime factorization, of n. Next time, well, we'll do an examples tutorial type class next time. We'll focus on these two problems here. These two problems here can be proved with the aid of that product formula that we've just established now. So we'll look at these and maybe some other examples of using that product formula when I see you on Friday. Okay. Do have a read through that proof there. It's quite a long argument, and it's putting a number of things together. So you do need to read through it a few times to really follow it and get all the moves in it, I think.